Hello. A little introduction first. My name's Alex Bennée. I'm a senior engineer in Linaro's virtualization team. You can find me on the QEMU channel as ST Squad and on the Linaro channels as AJB Linaro. I mostly work on ARM emulation, but I've been known to dabble a little in KVM as well. And for my sins, I use Emacs. Oh yeah, okay. Let's start divisive. So let's just start by defining what we mean by multi-threaded TCG, in case anyone's not familiar. So TCG simply stands for the tiny code generator, and it's often used as a shorthand for whenever you're using QEMU as a cross-processor virtualizer. So basically running code for one instruction set on a machine that supports another. So currently QEMU supports around about 16 families of processors, some of which I've put up there. So unlike KVM, the TCG variant of QEMU has only one thread for all its emulated vCPUs. So this means the execution engine runs each vCPU in turn, and the result looks a little something like this. So this is my 8-core desktop, and single core is frantically spinning around as it emulates every vCPU in turn. All the other cores are looking fairly bored. So this is obviously a massive waste of resources. So when we talk about multi-threaded TCG, we're looking for a process model that looks a little bit more like this. So it simply refers to the apparently simple change of making each vCPU run in its own thread. And in an ideal world, each vCPU thread would be distributed to run on an individual core, so we'd maximize the performance of the emulation. In practice, the result might be a little bit more chaotic. So why do we want it? Well, part of the answer is that we live in a multi-core world. This is the humble Raspberry Pi. It's sold 5 million units since its launch in 2012. Its current iteration has a 4-core Cortex-A7 in it, all running about just under a gigahertz, and it's available for $25. Now, of course, the Pi is a bit of a toy machine, but the Dragon board here is a commercially available 64-bit ARM system. It's designed for prototyping. And the board provides a quad-core Snapdragon, and it's available for $75. Even the phone in my pocket is a multi-core device. The Nexus has a quad-core crate in it, and its setup looks quaintly underpowered compared to some of the phones coming on the market now, which have 64-bit octo-cores, and it's available for $300. Of course, it's not just about the devices that we're trying to emulate. This is my desktop. It's a fairly modest i7, which I bought when I joined Linaro, and it has 4 real cores and 4 fake ones, and it cost me around about $600. In the end, I spent more on the RAM than I did on the processor. Of course, if you're prepared to spend a few $1,000s, you can get something like this monster. Its main use case is building Android images, but it would be nice if it could auto-test those images at a reasonable speed as well. While we're on the subject of Android, as some of you may know, the Android emulator is based on QEMU, and supporting multi-core in the emulator is a key use case for Linaro. So while the last few decades have seen quite a phenomenal growth in processing, as Moore's law has held true, we're starting to see a tail off in the single-core performance. So while embarrassingly parallel problems can quickly take advantage of these cores, the problem for emulation is a little bit more complex. Other than pure performance, there are some other reasons we should care. Multi-threaded TCG would behave more like real systems. So while you have all your vCPUs sat on a single thread, there are behaviors that you don't see in emulation, which you will get compared to the real system. If you've got flawed software, it's much preferred that any issues you have with concurrency show up whilst you're doing your bring up on QEMU than when you actually have to debug it on real hardware. Also, as QEMU is a dynamic emulation, there are things you can do which are a lot harder to do in real hardware. So you can do additional instrumentation to investigate behavior. There's other fancy tricks you can do, like record and playback for debugging and reverse debugging. So again, you want a system that behaves more like the system it emulates. Another often talked about use case for QEMU is cross-tooling. So as a developer, I've spent quite a lot of time building things for the non-x86 world, so I'm quite familiar with building cross-compilers. The process has got simpler over the last few years, but there's still a lot of inherent complexity. Sometimes this can be addressed by using Linux User, which Alexander mentioned, but it's not without its warts. So after you get bin format set up and you make sure your chroot and your multilibs are all right, you can still get stymied if there's threads or signals that occur during your build. What I really want is I just want to boot an ARM development board on my desktop and have the full distro and all the usual tools with it. So now we've talked about why we want it, let's talk about some of the things that we need to address. So the two main ones are global state in QEMU and the way that we model the guest memory. So when I'm talking about global state, this includes the numerous globals that we have during TCG code generation. There's also a number of runtime structures that are used whilst we're running the TCG code. And finally, there are structures that are associated with device emulation. The other thing that needs attention is guest memory behavior. While you've got vCPU scheduled sequentially, you get a lot of this behavior for free. As soon as you've got threads free to run across multiple CPUs, you actually have to take some specific care that you're meeting your guest memory semantics. So memory consistency also becomes a challenge because load store order is often only consistent for the CPU that you're running on. And currently QEMU ignores any explicit guest memory barriers. So let's look at some of the ways we can tackle this problem. There are three broad approaches. First, the classic approach is you split into threads and you stick mutexes around anything that's shared. However, you have to take care when you're doing this because it's easy to get into situations where you get deadlocks or you have lock contention that's so high that the system spends all its time thrashing around. Another approach is to accept the limitations of QEMU's TCG implementation and contain them in multiple processes. So each worries about emulating a single core. So this diagram comes from a project called QEMU, which is a research project that uses QEMU's code base with an arbitration IPC layer and shared memory. There's variants of this design that are used by some people that are doing processor emulation that talks to things like FPGA simulations and that sort of thing. Finally, you could accept that QEMU's original design's assumptions are incompatible with SMP and rewrite everything in a shiny, brand new code base. Because you know, of course, that this time you'll get all the behavior right and you'll make sure you've covered all the special cases. So, in summary, while the classic threads approach should give you higher performance, you have to be careful with your locking strategy. Having separate processes makes it a bit easier to get correct behavior, but it does require a potentially invasive remodeling of the code, and performance can be an issue. And while it's often tempting to rewrite things, remember the QEMU code base is 1.6 million lines of code. Slot count estimates it's around 260 person years of effort to get to where we've got to today. So you'd be throwing all that away. So what have we done? The current work uses the existing code base, obviously, and uses threads, but it tries to minimize the number of locks involved so we don't get exploding complexity. The run loop is mainly serialized, but the actual translated code is fully multi-threaded. At the same time, we've introduced some new memory semantics to help with properly emulating some of the guest memory behavior. So let's look at the global state. So the first major challenge is the code generator itself. There are a large number of per-file static variables which are used in the code generation path. If two threads attempt to do code generation at the same time, things can get very confused. Outside the code generator, there are structures that the wider system uses while the code is running. So this includes the soft MMU TLB, which needs to be updated when page mappings change. There's a jump cache that's used for looking up new translation buffers, and a couple of condition and flag variables. The condition and flag variables are fairly simple to make per vCPU. So this includes a hold condition variable, which is used to block the vCPU on pending work, and an exit request, which raises a flag to bring us out of the translated code. So now I've mentioned basic blocks, let's just quickly remind ourselves of how TCG works. The process is fairly simple. On demand, we take a block of machine code from the target, it's converted into an intermediate form, and then the final jittered code is generated. So here's some simple input machine code. It's a very simple subroutine which increments a value, and the branch return signals the end of the basic block. In this case, it's an unconditional return, but any control flow change basically ends the current input block, and that includes conditional branches and computed jumps. These are broken down into an intermediate representation known as TCG ops. So they're similar to the sort of thing that a compiler would generate, and then it goes through a basic optimization phase where we remove things like dead assignments and constants are propagated, that sort of thing. Finally, we output this binary code for the target machine that we're running on. I've simplified this example somewhat because I'm leaving the details of the soft MMU for later. The final code is wrapped up into a basic block, which consists of a short piece of prologue code, the translated code, and then we have up to 2 possible exit paths. In this example, we never use the second exit path. Finally, as the code runs, these blocks are chained together and jump directly to each other. This only actually occurs when we're operating in the same guest page, because jumping out of the page may require looking up a new translated block, because the mappings can change. So let's just remind ourselves of what global state we need to worry about. We have a bunch of globals used during code generation, and we have some global runtime structures which any vCPU might affect. So fundamentally, the translated code itself is safe when it's doing simple computation. Anything that it updates, it only updates the internal structures for that vCPU. So we really only need to worry about protecting things when we leave the generated code. So let's look at some of the reasons why that might happen. So the 2 cases I'm going to look at are returning to the main run loop or calling a helper function. So there are 2 principal exit paths to the run loop. The first is when we don't have the next block patched for the jump, and this might be because it doesn't exist yet, or a computed jump or something that needs to cross a page boundary. And the second case is where the vCPU has been signaled to exit. So this is typically done when there's an interrupt, but other things can signal an exit as well. It's actually also possible to asynchronously exit the run loop on a signal and jump straight back to the run loop. So this shows a simplified version of the run loop. The full version is a lot more scary. As you can see, we're running in a loop around here. We find a block. If we can't find it, we need to generate it. Once we've generated it, we run it, and we jump into the translated code. At some point, we will come back. So the first thing we've done here is in this code generation phase, it's all protected by a translation lock. So this means that we've effectively serialized all the code generation. So only one thread can be generating code at a time. That's a relatively quick process, and once you're running the translated code, you're fully multi-threaded. The second case is helper functions. So helper functions are called directly from the translated code, and you can call them for a whole number of reasons. Often they're used to do an operation that would be very fiddly to do with the TCG ops themselves. So, for example, most of the SIMD and floating point instructions are implemented by helpers. However, a number of instructions have an effect on system state. So an example would be a system TLB flush. The first case is fairly simple. As long as the results are private to the vCPU, no locking is required. If the results affect the status of other vCPUs, we need to use some sort of locking. However, there are operations that will affect all of the vCPUs. So we could use locks to do most of this. However, you have to be careful. If you're using a lock to protect a structure that's frequently read, then you're going to start killing performance. If you're going to use locks when you have to modify lots of vCPUs, that can quickly get very complex. So another approach is we can just ensure that the vCPUs have come to a halt and then do the changes that we want to do at that point. I say at leisure, it all happens fairly quickly. So QEMU already has a deferred work system. Work can be added to a queue, and then the vCPU is signaled to stop. Once it exits the run loop, it will process the work. So for the multi-threading work, there's been a new queue introduced called the queued safe work queue. This works pretty much the same as the other one, but it waits for all the vCPUs to stop. So this is useful if you want to process system-wide events. So in summary, for the TCG, we've moved some of the variables into per CPU structures. The translation lock is used to protect all the code generation and changes to the various runtime state. And finally, there's a new safe work mechanism which can be used for work that needs all the vCPUs to stop while changes are made. Now let's have a look at the way memory behaves in emulation. So the TCG currently doesn't offer any atomic primitives. So as a result, the actual code generated will be a load-store pair inside a basic block. With the current single-threaded behavior, basic blocks always complete before the next vCPU is scheduled. So this means any load, modify, store sequence is automatically atomic, as no other core can be running at the same time. Even on weakly ordered systems, loads and stores still on a program order for the CPU that they're running on. Once multiple threads are involved, each potentially running on a different CPU, all these assumptions break down. Code which worked thanks to your implied atomicity before will fail. Memory ordering also becomes an issue, although you tend not to notice it on the general case of running on x86, because the back end is strongly ordered and this masks a lot of the undesirable behavior. Now, of course, well-written guests will use processor features to mitigate this. So let's look at one of those. Load, link, store, conditional are a pair of instructions that are common on a lot of RISC systems, anything basically with a load store architecture. This is in contrast to something like compare and swap, which does a load, modify, store all in one instruction. So the key thing is the store will only exceed if the address loaded for earlier hasn't been touched by any other CPU, even if the value remains the same. The nice thing about load, link, store, conditional is you can emulate all your other atomic primitives with it. So introducing these proper load, link, store, conditional semantics into QEMU is important so we can model the load, store, exclusive and atomic instructions. But doing this in a way that doesn't rely on any intrinsic backend support is also important because we want to support all of our backends. So the first step is we introduce a couple of new TCG operations for the load, link and conditional store. Before we go further, it's worth reminding ourselves of how the soft MMU works. So let's talk a little about the implementation. The soft MMU is responsible for mapping all the memory accesses to real memory on the host. The mapping is actually done by simply adding an offset to the address, and this will point into some real address in the QEMU address space. The fast path is all implemented in generated code, and then there's a slow path that will fall back into the C code, and eventually this ends up walking the system's page tables. So I've drawn some nice diagrams to show what happens. Each access to the memory contains 3 attributes. So there's the address itself, there's a MMU index, and then there's an access type. The MMU index here isn't directly related to the privilege level that you're running. For example, there are some MMU modes that allow you to access kernel and user space at the same time. So the first thing we take is MMU indexes into the table that we're going to use. Given the right MMU table, we then generate an index into the TLB. So the size that each entry of the TLB covers is driven by the number of MMU modes we have, because the total table needs to fit into a reasonable amount of space. But in general, at least be an 8-bit index table. Finally, the target of the guest address is masked out and compared to the entry in the TLB table. If it matches, the offset is applied. If not, we fall back to the slow path. So in the case of doing a bunch of operations in the same page, we'll do the slow path once, and then all the following operations will just keep using the entry. These flags are quite important, though. You can set flags in the lower bits, and this will cause any match operation to fail and force us into the slow path, and this is quite useful. So how does this help with load, link, and store conditional? So we've already introduced our front-end TCG ops. So using the soft MMU slow path, we can then implement a back-end, implement the back-end for these operations in a fairly generic way. We do this by introducing a new TLB flag. So when a load link operation occurs, we set a TLB exclusive flag for the page that we're in. And then when the store conditional occurs, it sees that the flag is still set, and then that succeeds. After the load link store pairs happen, normal loads and stores can just happen as normal. It doesn't affect the slope, doesn't affect the performance. If you do a load link and then some other CPU then does a write, because this flag is set, it will force the slow path, and then we'll go through all the slow path and the MMU helpers. The MMU helpers will then flip the exclusive bit, and when the store conditional occurs, we know that some other piece of memory is accessed. Sorry, some other process has accessed the memory, and then store conditional will fail. So in summary, we've introduced a new flag. We can force all accesses down the slow path whilst the flag is active. We trip the exclusive flag, and then store conditional knows whether or not memory has changed. So, in summary, the soft MMU does offer us a fairly efficient way to map guest memory into the host, and at the same time, it provides a fairly efficient way of trapping access to certain regions of memory, which we can use for many things. In this case, for implementing our load link store conditional support. And this doesn't overly burden our normal memory access. Memory barriers, however, are still an issue. So finally, let's look at device emulation. Good news, KVM's already done it all for us. The KVM model is very much relies on having a thread per vCPU, so they had to add thread safety to a number of systems. This included adding a memory API, so all accesses to the emulated device can be properly serialized with locks. The other big change was introducing an I/O thread, which involves separating the handling of I/O from the rest of the system. So for TCG access to device memory, all the MMIO pages are flagged in the soft MMU TLB. So as you already know, this will force a slow path. This goes into our memory API. And then the memory API defines a region of memory as either being lockless or locked with the BQL. By default, pretty much everything's locked with the BQL. But if you've got a device emulation that's going to deal with its own locking, you can have a lockless entry. So, thanks, KVM. So, let's talk now about the current state. And for this and the little performance and demo slides, I'm going to hand over to Fred.
Hello, everybody. I'm Konrad Frederic, but you call me Fred. So I want to show you some GreenSox MTTC proof of concept and some benchmark results. Like that? Ah, sorry. So first I would like to introduce GreenSox a little. So it has been created in 2005. Our mind focused on the open source hardware simulation. We have our own open source system library, which is called GreenLib. We also build platform and models for our customers, and we contribute to QEMU and System C, hence MTTCG. So it's a proof of concept. I wanted to keep it simple, so we just run a little build root system, custom one, on a vExpress A15 virtual machine. So the goal is to check that all vCPU have their own thread and check if the performance is really better. So I will try to find back my okay. So here we go. Not easy. So we run some hashtop just to see what happened with the MTTCG thread. Oh. Here we go, and actually we have the current QEMU MTTCG running. So we can just run two JSON at the same time and check how many time it will take. Here you can see that both vCPU threads are full loaded, and both host CPU was full loaded as well. You can see as well that we take approximately 6 seconds to achieve this current test. So that's pretty fast. If we run only one JSON test, we can see that only one vCPU thread is fully loaded. So in fact, that means that the JSON run only on one vCPU in the guest. And we can compare all that with upstream QEMU. So we have only 3 threads because, of course, MTTCG create another thread. And if we do exactly the same command, the same command line, you can see that you have only one thread fully loaded, which goes on both vCPU, both host CPU. Finally, take approximately 30 seconds which is approximately twice as the empty TCG. So is the performance really better? Yes, I guess. I took some number with several tests just to have more precise results. I run the test with 1, 2, and 4 vCPUs, and then 1, 2, 4 instance of Drystone, just to check. From this table, we can extract the last line. We do 4 parallel Drystone for 1, 2, and 4 vCPU. Then we compare with upstream. We can see that the red line is empty TCG. The time is highly reduced compared to upstream. We are 63% faster with 4 vCPU and 45% faster with 2 vCPU, which is quite good, I guess. However, the test is ideal and doesn't benchmark all the part of empty TCG. For example, all the TLB maintenance operation, which are quite slow if we exit when we do that. Same for TB invalidation on TB flush. And then the multi-thread safe TCG atomic instruction have not been benchmarked with this test. Additionally, if we take only one Drystone instance, we can see that multi-thread TCG is a little slower. For example, for 4 vCPU, we have 4% of overhead. This might come from locks, maybe. Okay. And as a conclusion of this result, personally, I won't make a live demo anymore. It's too stressing. And for empty TCG, you can say the performance are better. We know why we do that. It's good for the increasing parallel tasks in new guests. But we have more test case to do, especially for all this TB, TLB flush, etc. We might want to log the number of occurrences of this operation and measure the time it takes while comparing it to QEMU upstream. We hand over to Alex. Good.
There we go. Excellent. Right, so let's just quickly talk about what's left. So I'm going to talk about the state of the load, link, store conditional patches, the multi-threaded TCG patches, memory barriers, what we need to do for the front and back ends, and testing and documentation. So the majority of the load, link, store conditional patches are actually independent from multi-threaded TCG. There's only sort of 2 additional patches needed on top to enable it for the multi-threaded case. It's already been through a number of review cycles, and we hope to be able to get it merged soonish now that the tree is open. The work on that has been done by Alvis Rigo of Virtual Open Systems, and you can see his work. There's also a MTTCG branch as well up there. So for the Fred's multi-threaded TCG patches, they've gone through a lot of cleanup. They've been through several rounds of review, and we're starting to get some of the simpler cleanup ones get pulled into the maintainer trees. So this means the delta between mainline and enabling full multi-threaded TCG is going to reduce. So as you see, Fred did the work from Green Sox, who have very generously sponsored him for the last 6 months to work on this. Memory barriers. There is no code yet to deal with memory barriers. We've got a proposal that introduces 1, 2, maybe more TCG ops to represent the memory barriers. However, this is a case that most people don't see, because if you're running on an x86 backend, you probably get away with it. The pathological case, of course, is running x86 on a weakly ordered backend, and whether or not that's ever going to be practical remains to be seen. So the current testing has mainly been focused on ARM32 on x86, but we want to enable it on all front-back-end combinations. Each front-end that needs to support, that wants to support multi-threaded TCG will need to have their atomic semantics updated to use the new TCG operations. And if we go for TCG operations, the memory barriers, each backend will also need to support the memory barrier operations. So this might require having an incremental approach where only some combinations build for multi-threaded TCG at the start, and then as each front and back end is converted, we can turn it on. Testing and documentation, both are important. I mean, this is a potentially invasive change to QEMU. We want to have a broad array of tests. We've already got a number of hand-rolled tests, and we've been starting to build up a number of KVM unit tests, which now accepts TCG as a first-class citizen. They're mainly torture tests, so they're really to hammer all the various flushing cases and make sure we've not got any deadlocks in the locks. And also, we want to have a final design reference for how a multi-threaded TCG works in the docs directory, so no one has to guess about how it works. So with that, are there any more questions?
Hi.
Hi.
Do you forecast to use empty TCG with KVM and a real MMU to improve performance?
Is this the... So this is running TCG code but using KVM to do the memory mapping? Yeah. I've dreamt about it from time to time, but it's been nothing more than a dream.
Hi. So did you already try self-modifying code on it, or such a thing, so that one vCPU would actually invalidate another's vCPU translation block?
Yeah, I mean, you can trigger that by doing things like TLB flushes that will flush all the code entries, and then our torture tests do exactly that.
Okay, and do they also try to do that with incoming exceptions, for example, given a division by zero or such a thing?
No, not yet, but that's a good idea to add.
So you said your load link store conditional is effectively managing the reservation at page granularity. My recollection is that most real CPUs manage it at cache line granularity. Does that change mean you could get more store conditional failures?
Right, so for an architecture like ARM, the granularity of the protected region is a implementation-defined number. And I suspect, from a performance basis, yeah, you just have to go with what granularity the TCG has, rather than try and do lower ones. So you do run a risk of having more bounces on your atomic operations because some other unrelated thing is touching well above it. Any more questions? Okay, well, thank you all very much.